So the point of this lecture today is to start talking about the challenge that you have of getting from dead, inactive system sitting on your desk or in a room or something like that to applying power and getting software running on it, because that's no small feat. In fact, when you look at how primitive and simplistic machines are at that very early stage in their execution. So bootstrapping is basically the process of figuring out how to get code running on the computer, code that actually solves people's problems. So as the slide says, all computers have the same basic issue. They need a program to know what to do, but they have no program. And so you have to figure out a way of getting the program that you want to run onto the computer. So that's where bootstrapping comes into the picture. It's a term that originates, probably many of you are aware of this already, but this concept of pulling oneself up by one's bootstraps, which is sort of, ironically paradoxical in its characteristic, but it sort of started becoming applied specifically in the context of computer systems to sort of reference this kind of issue of getting the computer running. Okay, since we have ROM, read-only memory, let's just say that we have integrated circuit memory, which is fantastic because you can cram so much information onto an integrated circuit now and plop that into your computer somewhere and start running the code that's on that IC. That has basically made life wonderful for getting things running that are useful on a computer. But we didn't always have memory, and I always like talking about these historical things, but I've taken out a lot of the detail here just for the sake of time. Before we had read-only memory, computers would have sort of hardwired mechanisms for specifying the initial boot up tasks for getting the computer running. And when I say the initial boot up tasks, I'm talking unbelievably primitive. We're talking so simple. Here are a few examples. You have punch card reading computers, which we're all aware were a thing because we've heard of punch cards and the fun of like carrying your stack of punch cards and tripping and they go everywhere. So you draw a diagonal line across your punch card so that you can keep them all in the proper order and all of that kind of fun. But the computer would have a hardware mechanism where it would read one card that contained like a small handful of instructions, and then it would start running that. That would be how it would boot. Or some computers would have banks of switches that you would configure the switches to specify anywhere up to 10 instructions to start running the computer. I mean, can you imagine setting all those switches to do that? And then there was another mechanism that was used for quote unquote read-only memory, which was called a diode matrix. And if you ever, like me, I love vintage compute hardware, partly because the stuff I grew up with is now becoming vintage. But a diode matrix, you can get on eBay and search for diode matrices. And basically, they were arrays of diodes wired together, and people would go in and snip out diodes to make zeros. And if you left the diode there, then it was interpreted as a 1. So this was a mechanism used for specifying the initial instructions to run in the computer. That's really hardcore. That's like low level. And so because you only had a very few instructions, that set of instructions would have to start the next thing, which would hopefully be more sophisticated. And then that thing would load the actual program that you wanted to load and run. So you can see how you have this incremental process of growing more sophisticated, i.e. pulling oneself up by one's bootstraps. Now, once we had integrated circuit memory, particularly read-only memory, so either it would be one-time writable read-only memory where you basically burn the ROM and then it can never be changed, or we started getting into erasable programmable read-only memories, and that gave us more flexibility to fix problems, and because software sucks, right? We always have bugs in software. It allowed us to start having much more sophisticated programs on the computer so that we could offer more and more sophisticated capabilities to users of the computer. And so we started even having basic disk driver support so that we could get lots of data off the disk, basic video so you could actually switch into graphics modes and start doing things in graphics. And it's only gotten more sophisticated over time. Now, that software that sits in persistent memory has a name. We call it firmware because it's on an integrated circuit, right? And so the firmware is a really important bridge to getting to being able to run arbitrary software on our computer systems. A lot of times it contains drivers, it contains basic configuration and basic operational code to get things up and running. Now, I mentioned that we have gotten more sophisticated in how we manage this persistent memory. And now many systems use an electrically erasable read-only memory, which is not too different from what your solid-state drive uses. And you can reflash that memory, which means that you can upgrade your firmware. And I want to sort of mention right here, this is insert the public service announcement. Make sure that you update the firmware on your computers, on your access points. That's always one thing that I do anytime I go to somebody's house to help with their networking infrastructure. I check the firmware on their access point, or I check the firmware on their printer and things like that. Make sure you keep these things up to date because they find bugs. And sometimes they're security holes, and you definitely need to keep those things patched. So how cool is that? And not only that, I'll just mention, even though I don't have time, that we use this when we send probes out into space. We send, spacecraft to Mars and other planets. A lot of times the software isn't done yet, and it's stored in firmware, and you have firmware updates that are being beamed out to these probes on the way. So this ability to rewrite the firmware on a device is really empowering, and it's used heavily across the board. Sorry, I'll stop geeking out about that. Now, since we're working specifically with x86 processors, and you can see that I have IA32 here. It's all over the slides. IA32 is the 32-bit instruction set architecture for x86 processors. And that's what Pintos uses. When we run Pintos, and actually that's what the Linux virtual machine also uses because it's a 32-bit VM image. IA32 is the most relevant x86 instruction set architecture for this class. There's another one that came after you may be aware of called x86-64, and that's a bit beyond our capabilities for this class. But if you were going to look at modern systems programming, that's what you care about is x86-64 because that's what is used on modern, general purpose computers that we use every day. Or I should say that until Apple changed over to the M1 silicon. So it was like I still have an Intel Mac, so it's still relevant to me right now. Okay, so computer manufacturers will put a read-only memory on the system, on the motherboard, that basically gets activated when the processor boots and starts running instructions at this address. You can see that it's got like 16 bytes left before it hits the top of the address space. And so the ROM will have instructions there that get to run. And almost always what it is jump to the real memory, like jump to the real start of my firmware. That's all you really have space for in that 16 bytes. So it's not really a surprise. Also, the processor starts out in ring 0. We talked about this last time because the bootloader, being the first stage in loading the operating system, needs to be able to do whatever it needs to do to the compute hardware. And a lot of times on our older systems or on backward compatible systems, we need to be able to go from the old archaic x86 or 8088 memory addressing modes and execution mode, switch over into modern protected mode execution. So that's one of the things, and you can only do it from ring 0. And so the bootloader needs to be able to do these kinds of things. Now, there are two categories of bootloaders right now. You have PC BIOS. This is, again, what Pintos uses. And you also have EFI or UEFI systems. Most of your modern computers, if you bought one in like the last 5 years, are probably using UEFI and using UEFI bootload mechanism. Although it's still possible that you may be using BIOS at this point, because EFI adoption has been going somewhat slowly, and for reasons that I hope I have time to talk about. Okay, BIOS was the first firmware for x86 computers, and it was basically the toolkit that software had to use on top of the hardware when it had just been started up. And so it would be provided. There was a company that was very famous for doing this called Phoenix, and there were a few other companies, and they would provide BIOS to allow you to interact with the hardware when you were in this very primitive Bootstrap environment. Okay, so yeah, you have a bootloader to start the Bootstrap process, a library of operations that you can use for talking to the screen, talking to disks, talking to the keyboard, doing simple junk like that, finding out how much memory is in the computer and so forth. So you have these simple operations, and you can see why it would be called BIOS, basic input output. And then also a lot of times BIOS would include a UI that you could drop into if you like hold down delete during Bootstrap, or control F8 or whatever, like Alt Shift, scratch your right ear, whatever it takes to get into the BIOS config. And you could use that to tell the BIOS things that it can't figure out on its own. Fortunately, that's almost never necessary any longer. Okay, and this functionality wasn't really specified formally. That's what I mean when I say it's a de facto standard, because what happened was the original IBM PC was designed and built, and it had this BIOS mechanism, and then you had DOS coming onto the scene, and obviously DOS needed to use the BIOS API calls, and then other people started building PC clones. And in order to let software run on the clones, they had to implement the same features using the same BIOS calls, the same argument passing mechanisms. All of that had to be the same. So just by virtue of everybody trying to get the same software running on different pieces of hardware, people figured out, reverse engineered the BIOS capabilities, and then that sort of became widespread at the time. So that's what we mean when we say a de facto standard. Okay. Now, bootloading is simple in BIOS. Basically, if you reset the computer, and a lot of times that would be like power cycle, or you push a button on the computer to reset it, that would be a hardware reset. And what would happen is there would be a self-test run called a post, because it's a power on self-test. Check your memory. You'd get a disk seek sound out of your hard disks and your floppy drives. It was all very exciting. It would always do. And so that concludes, and then the BIOS starts looking at what peripherals are available. And when I say peripherals, I mean disk drives, and how do I talk to the screen? Basic stuff. Do I have a PS2 mouse connection? Do I have a USB mouse connection? What do I have to talk to the basic, most primitive computer peripherals? So then what happens is BIOS would go through all of the bootable devices. So what that typically would mean is floppy drives first, then hard drives second. But that obviously is very different now. You can configure it to be whatever you want, and it'll include USB drives, it'll include optical drives. You can even do network bootstrap now. You can do all these different things with BIOS. And so, yeah, as the slide says, it would load the first sector of each device into memory, and would look at the end of the sector's data. And if the end of the sector had these two values, 55 hex and then AA hex, it would say, I assume this is a bootloader. Surely that could never happen in real life unless someone meant to. So it would see that signature, and it would go ahead and load that and start running. Okay, so it would load this boot sector at a specific address. You can see it on the screen there, 7C00. This is not important for this year's CS124, but it would load it at a specific address and then jump to the address to start running the bootloader. Okay, and so that means you have 510 bytes to do whatever you need to do to load the operating system. Now, it may be that your goal is not to load the entire operating system. It may be to load the next stage of the operating system. Because it turns out you can do a lot in assembly code in 510 bytes, but you can't do a lot in assembly, in like a high level language in 510 bytes. So you would typically write bootloaders in assembly code. Okay, BIOS also would pass a few details to the bootloader, like what drive the bootloader was loaded from. This is important so that you can know what drive you should continue fetching data off of, because how are you as the bootloader supposed to know if you were loaded off C:, or E:, or A:, or whatever? I mean, how are you supposed to know? So the BIOS has to communicate that information to the bootloader. Okay, yeah, so I already talked about this. You can see this is incredibly small and primitive, a mechanism, but it allows you to continue loading increasingly sophisticated programs into the computer memory. Now, another aspect of this that had to be navigated was the issue of disk partitions. I imagine that probably many of you have dealt with disk partitions before. Maybe you have Linux systems where you just said, hey, Linux, configure partitions for me. Like on my Mac, I have 2 partitions because I, for a short period of time, was dual booting Windows and Mac OS. Now I'm like, that's too complicated. I'd rather just run Windows in a virtual machine and use shared folders to interact with the host OS. So I am about to go back to 1 partition, but this is not uncommon to have multiple partitions on larger drives. And so the first sector in the BIOS universe would be this thing called a master boot record, which would say, here are up to 4 partitions on each device. Now, there were mechanisms for chaining these so that you could have more than 4 partitions if you needed to, but the initial design was just 4 partitions. And so notice what I say here. Each partition could be used for a different OS. Okay, that's interesting. Or an OS could use multiple partitions. So you now have the master boot record residing where the bootloader should be, and you don't know which OS to load. So the MBR has to do something clever, okay? Now, yeah, and the OS bootloader would be in the first sector of that partition. It wouldn't be in the master boot record position. So the other thing that was challenging about partitions is that the partition information takes up more space in the master boot record. So you can see I have here 4 partition table entries would take about 64 bytes. And so if you had an old style master boot record, you'd have 446 bytes to do the next thing. But the problem is, as things became more sophisticated, the master boot record became more complex as well. And so you would be down to like 434 bytes of space to do your boot loading. And it would be in 2 pieces because the partition table had to be at a specific location in the MBR so that the BIOS could see it. So it's like, oh, this sucks. Okay. So you can see that if you're using something like Grub, and maybe those of you who are using Linux or doing multi-boot, you might be using NT Loader or you might be using Grub. Clearly, that's not enough bytes to provide all the sophistication of these bootloaders. And so the bootloader itself would be 2 pieces. You'd have the first stage, which basically its only job is to suck the second stage into memory from somewhere. And then the second stage is where all the magic actually happens, okay? So this is complicated. Like building this process of getting the computer stood up is actually quite complicated. And this is only the beginning of the picture, it turns out. Okay, so the way that these MBR loaders work is using a mechanism called chain loading. And chain loading is kind of a neat thing. Basically, the MBR acts like the BIOS because the OS loader on the partition, it doesn't want to know that it was loaded by the MBR as opposed to by the BIOS. And so there's a pretty simple mechanism. Basically, the MBR just loads the next bootloader into the same address that the BIOS would use. And then the MBR loader jumps to the start of it and lets it run. Okay, so it basically emulates the exact same process that the BIOS loader follows. The only problem, of course, is that the MBR loader was there and now can't be there because it's loading something else there. And so a lot of times what you'll see in these Bootstrap programs is what they'll do is they'll have code to copy themselves somewhere else in the address space, jump to it, and then start running from there. And I don't know how many of you will appreciate the complexity of that, because you may have programs that access variables. I mean, we all write programs that use variables. That part's not hard, but the variables have an address. And not only that, but if you have statically allocated values like global variables, things like that, then they're going to be assigned a specific address. And so these bootloaders need to be able to run part of their code at one address and another part of their code at a different address, with different offsets and everything. So all of this is quite challenging. And so you can see that it's a fun puzzle to try to figure out how to build a bootloader. It's also irritating. And thankfully, we don't have to do this anymore for the most part. Okay, so what is the bootloader doing at this stage in its execution? Well, it's relying on the functionality provided by BIOS, or the BIOS. It doesn't really matter how you say it, but there's BIOS functionality that's being utilized at this point to interact with the compute hardware. Okay, and bootloaders need to have a way of invoking BIOS operations without knowing precisely where they live. It's the same issue that we talked about with system calls. Application doesn't know where in the kernel a system call resides, so it uses this indirect invocation mechanism using a trap and simply setting the operation to perform in a register. Well, same thing with programs running in this environment using BIOS calls. You use a software interrupt mechanism, and this is a simple example. Different interrupt numbers would be assigned to different kinds of functionality. Int 10 hex, or I guess that would be 16 decimal, would be used for interacting with the display. Int 13 hex would be for interacting with storage devices, and so forth. There were various interrupt numbers assigned to different kinds of tasks. And you would say what operation to perform. Like I have here, for int 10, it would be AH. You would say, write me a character, clear me an area, do these, switch me to a different color. And so you would do that kind of thing and then invoke int 10. That would go into the BIOS operation. BIOS would do its thing, and then you'd return back. Okay, so this is a simple example of printing a character to the console. Okay, now I want to kind of mention here, it's not really accurate to say you're trapping into anything at this point, because the environment in which BIOS executes is so primitive that we don't actually have protection levels. I mean, I mentioned that we're in ring 0 because Bootstrap code can do whatever it wants, but we're not actually in a protected memory type execution environment yet. We're in a very primitive environment. So you're just using int as an invocation mechanism, an indirect invocation mechanism. And then IRET just takes you back to the code. And that's all there is to it. You're not switching protection rings because none of that's been set up yet. Okay, now this is one complication of the OS loading environment, is that the BIOS operations depend on this old and archaic memory addressing mode called real addressing mode. I mentioned it here. Yeah, ancient is probably right. When did the first 8086 and 8088 come out? I think we're talking late 70s, early 80s. So I was just a wee lad. I was born in 75, and I had my first computer, which was a PC-AT clone, in about 87, 88, something like that. So, and that was an 8088 processor. And real addressing mode was the only addressing mode we had. That was just it. So the BIOS came to be in that environment, and it was never really updated as computers marched forward because there wasn't a big reason to do so. IA32 supports multiple memory addressing modes. As far as I'm aware, x86-64 has the same addressing modes. They're pretty sophisticated now, and we are only really seeing incremental extensions at this point. So there are really advanced things like protection for memory. You can't execute from this region of memory. This has to be used for data. It's read-write. This has to be used for code. You can execute from it, but it's read-only. You can do that stuff in modern memory addressing modes. But the old stuff didn't support any of that. And it's only provided for backward compatibility. That's one of the big constraints of this whole processor family, is trying to maintain backward compatibility. So really what the OS wants to do is to get into the advanced and modern, sophisticated capabilities of the processor, where you can do all the fancy stuff that we depend on, but at that point you can no longer use BIOS. Now hopefully you're looking at that and saying, well, if you can't use BIOS anymore, the OS needs a way of talking to the screen. The OS needs a way of talking to disk devices and solid state drives and the keyboard and everything else. So you can see that certain things have to happen in this Bootstrap process of device discovery and making sure that you know what's there and you can take over when you no longer have the BIOS capabilities to depend on. Because the minute you switch from real addressing mode to protected mode, you can't use BIOS anymore. Okay, so yeah, this is what I was saying. There's a couple of issues. One is this memory addressing mode, which I'm not even going to describe. I mean, it's, I suppose, fun to know about, but it is archaic and it is anachronistic now. You don't really need to know about it unless you write a bootloader. BIOS also has a different way of dispatching interrupts, and I should be careful how I say this because in real addressing mode, there is a different way of dispatching interrupts than in 32-bit or 64-bit. The interrupt descriptor table entries get larger and have more information in them. The primitive real addressing mode has a very simple interrupt dispatch mechanism. Okay? So basically, from the point you switch into protected mode, you have to start using device drivers that you have provided or someone has provided for you to interact with the computer hardware. You no longer have the support of this BIOS mechanism, okay? And this is actually kind of important for a number of reasons. A simple one that I'll mention here is that a lot of times BIOS does what's simple, not what's fast, and not what's sophisticated. And so the OS often wants to step in and reinitialize devices so that it can start doing things that are a lot more sophisticated. I'll give you a really simple example. A lot of times when you want to read data off the disk, that's a slow operation. I mentioned before, that could be like 30 million clocks if you're talking to an older or slower like laptop hard disk. So if you're going to spend 30 million clocks waiting for data to come back, OSs are clever. They'll set up the data transfer in the background and go do other things. BIOS doesn't have anything else to do. BIOS is simple. And so BIOS will, go ahead and do the access and just wait until it's done and the data is in memory. And then it'll say, here's your data. And so we don't really want to use the BIOS mechanisms for interacting with devices. We want to use some of the faster, more sophisticated mechanisms anyway. Okay, so this is just a summary. I'm just going to throw this up here. So power on, we have the processor is hard-coded to start running instructions at this particular address. We plop a ROM there to intercept that and to go to the real bootload code or bootstrap code, initialize a few devices, be simple about it. We load the first device's boot sector. The first device that we find that has a viable looking boot sector, we start running it. Maybe that thing chain loads to some other bootloaders. And eventually we suck the OS into memory and that thing initializes the hardware the way it wants and takes over the computer. And that bootstrap process sort of is shed at that point because it's no longer necessary. Okay, so that's the BIOS bootstrap process. Are there any questions at this point? Well, if there are, you can go ahead and ask in the chat. Otherwise, I'm going to continue on. I get so excited about this stuff. I have to make sure we cover everything in the lecture, the slide deck. So there was an issue that occurred with this, which is that BIOS is only for the most basic type devices and functionality. Like there was no support for printing to a printer via BIOS. It's like, why would I support that? There was no functionality for talking to a network card. Like, why would I expose that in BIOS? And so the OS early on would have to figure out what other devices are available on the computer. And earlier PCs would do this by probing specific memory locations and IO ports to figure out. It would be like, it'd open a door and shout into the room and listen to see if it heard anything, shout back. And if it didn't, it'd be like, okay, I guess there's nothing there. And it'll go open another door, shout in that room, anything? Yes. Okay, that device exists. And it would have to do this process to figure out what's in the computer. Now, this is slow because devices sometimes take time to respond to you. Like you'd have to wait a certain number of clocks and then read another port, blah, 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 blah. So the other issue is that sometimes you would have multiple devices that had similar ports that they used. And you would probe for one kind of device, but there was actually another kind of device there, and it would lock up your system. So that really sucked. And I remember having to deal with all of this stuff as a college student, and it was just really irritating. And so computer designers wanted to move to something that was a little bit easier for OSs to discover what's actually in the computer system. And so that's where this term plug and play kind of came from. We wanted a way to plug hardware in, not have to go rebuild the kernel, but somehow the OS could find out the hardware was there, ask it what it is, and then start talking to it relatively easily. Okay, so important advance, and I'm super happy I don't have to worry about this kind of crap anymore, because boy, it was a drag. So this required, among other things, an update to the hardware bus that was used in the personal computer. And there was a great question last in a previous lecture about, well, what is a bus? And besides being a bunch of wires, it's also how you use those wires. And so this is a great example where the protocol needed to be updated so that the processor could query the bus master and say, hey, who all is on the bus? And then it could enumerate those devices, and then it could ask each device, who made you? What are you? These kinds of esoteric, deep questions that we all think about. Like, well, what are you? Are you a graphics card? Are you a sound card? Just tell me about yourself. So the OS can now start using that kind of mechanism to enumerate the devices and load the specific drivers for them without having to do this crazy primitive like knock on stuff and see if it reacts. So these are some example plug and play buses. I'll just mention PCI and USB. The other ones, who really cares? But PCI was the first really prominent plug and play bus in x86 PCs, and USB everybody should know about, because if you have a USB device, you plug it in, you can actually watch the messages that are sent and received on Wireshark now, which is really interesting. You plug in a new device and you get messages from the USB controller saying, hey, there's this new device, and here, it's a block device or it's a character device. It does this stuff. And then the OS can respond accordingly. So it's very powerful. Now, along with this, the hardware started providing more information in other areas to the OS, like memory layouts and how many processors there are and other useful information like that. And so the BIOS would set up these data tables that resided at specific addresses. And if you want to see sort of an old school version of this, you can look up the Intel multiprocessor specification, because it had tables that would tell you every processor, the local APIC address to send interrupts to that processor, and so forth. So you could just find this table and know I'm on a multi-core system, and you would know how to talk to all the different processors. I could take a lot of time talking about that, but I won't. It's really interesting. One of the big updates that came was ACPI, and probably all of you have seen this acronym ACPI, Advanced Configuration and Power Interface. In fact, when you go into VirtualBox to shut down a virtual machine, one of the options is, perform an ACPI shutdown or send an ACPI shutdown signal. Well, this is the mechanism that was devised. I think this was late 90s. And so this is, again, a set of tables that allow you to know how to talk to the compute hardware. And this would be sort of populated during boot time. Okay. So there's a way of accessing it. I'm not going to spend any time talking about this. Fascinating, though. You have to hunt for it. And you know that you found it when a checksum computes correctly. And it's like, really? That's how we do it? So you can read all about it. It's quite entertaining to read about how ACPI works. But this grew into something that is actually looks like a good standard modern approach that people are settling on. And that's the Unified Extensible Firmware Interface. Okay. And UEFI is something that is actually usable after you've booted and after you've gotten out of BIOS, So you've gotten into protected mode, you can continue using UEFI. So that's a really valuable benefit of it. Okay. So let me see what I say here about this. UEFI was prompted by a project at Microsoft, which is why when you read the UEFI standard, you see a lot of Microsoftisms in there. And I'm just like, oh, because, I worked at Microsoft. I think Microsoft's a great company. It's done some naughty things like most companies have done. But a lot of its stuff has a certain aesthetic that I find unappealing. So I guess I'll just leave it like that. But Intel had this processor family called Itanium, and it was a 64-bit processor. It couldn't run BIOS. So you couldn't just plop a BIOS chip into the motherboard, but we still needed a way of booting it. And obviously Microsoft wanted to run Windows on it. And so they came up with this thing called EFI, which was basically a firmware standard that would sit above the hardware and provide the capabilities that were necessary for OS bootloaders and operating systems themselves. And so like it says here on the slide, UEFI is a firmware interface standard. So BIOS emerged organically, let's say, by virtue of people wanting to have software that worked on different hardware systems. UEFI is actually a formal standard, and it's quite extensible, that sits on top of the hardware and lower level firmware to provide OSs with the facilities they need. In fact, it provides all the memory mapping mechanisms. It already switches you into protected mode. It sets you up in a nice, clean environment so that you can write an OS loader without too much pain. There's a little pain. I'll mention that briefly. Okay, so UEFI is modular. So what that means is you can provide OS facilities or pre-boot facilities as modules that are installed in a special partition. Let me show you some more of those details. Yeah, so you can install UEFI bootloaders for OSs. This is something that an OS installer can do. Plop in the UEFI bootloader for that OS, and that knows how to load and run the OS. Okay. You can also have UEFI applications that allow you to do stuff to the computer before you actually enter into a specific operating system. So it runs in the special environment called the pre-boot environment. Okay. And it's kind of fun. VirtualBox supports UEFI. And so if you want to experiment with it and see the kinds of things you can do, you can always set up a virtual machine with UEFI. And there's like UEFI system explorers and things like that. And you can just poke around and see what is in the pre-boot environment. And then there's all kinds of UEFI drivers for talking to devices, talking to the network so that you can do network bootstrap, lots of powerful things. Okay, so really, really neat kind of system that was devised. Now, UEFI sort of subsumes a number of other standards, so it continues to expose ACPI tables, for example, and it also has tables like the multiprocessor specification, which is why, it is worth looking at if you want to ever write a multi-core operating system. But UEFI does something novel that wasn't done by ACPI, which is that it actually stows function pointers to operations in these tables so that you can invoke specific operations in the UEFI library support. So this is a simple example. I'm just going to try to show you this really quickly. Thankfully, we don't have any UEFI assignments, although maybe a future version of 124 will. But you can see EFI main. This is the entry point for the UEFI module. And you get an image handle and you get a system table. The system table is sort of the starting point for everything else in UEFI. And you basically say, I want to be able to talk to the console. So there's something in the system table called con out that allows you to talk to the console. And there is a specific entry, a function pointer to output string, the thing that knows how to write to the console. And basically you can say, output a string to the console. And this call would go ahead and do that. Okay. Everything in UEFI is Unicode. That's why you have char 16s everywhere, or car 16s. I don't know how people like to say this, but char 16s for Unicode so that you have internationalization support even in the pre-boot environment. So really clever. I think it's a really clever mechanism. Okay, let's see. Here's another picture. You can see you've got your platform hardware, and I mentioned that there's a special partition that is used for storing the EFI modules. And that's kind of a key detail. How do you make it extensible? You can't just load all that stuff into persistent memory, so you use disks sometimes. You can use solid state storage or an actual spinning magnetic disk to store UEFI modules. Okay. Typically, you have one small partition at the beginning of your drive for UEFI to use. It's called the EFI system partition. Okay. Macs have it. If you set up a Windows or Linux machine to use UEFI, it's going to have a system partition as well. Okay. All right. One more thing to tell you about, and I think we are quickly hurtling to a close. Another thing that's updated in UEFI is the way that partitions are recorded on the disk. You remember that I mentioned master boot records, 512 bytes. You got to cram a bunch of stuff in there, and it had a very primitive mechanism for recording where partitions lived and what kinds of partitions they were. Okay, the issue that I have described here, you have 32-bit values for MBR partition entries, and so given those constraints, you could have up to 2 terabyte partitions with the assumptions that I have on the slide here. I think there are more advanced MBR entries now, but why? Why would you do it? So the solution that was created as part of UEFI is this thing called GUID partition tables. You've probably seen this in various configuration utilities for hardware. It's like, oh, do I want to format with a GPT or an MBR? I don't know. So a GUID partition table basically is a much more sophisticated mechanism for keeping track of everything. GUIDs are globally unique IDs. They're generated 128-bit identifiers, and they are very likely to be unique because they take both time and space into account. How do they take space into account? They use the MAC address off of one of the network cards in your computer, because those tend to be uniquely assigned. And so that's how they take both time and space into account. So the partition descriptors can access monstrously huge partitions. Okay. Let's see. So I'm looking at this. A zettabyte is 1 billion terabytes. So you can have up to 10 billion terabytes in a partition. That should be enough for now. Okay, now all of the different details in the partition table are identified by GUIDs. And this is one of those things that was really kind of important because master boot records would use 1 byte to specify the partition type, which meant it was super easy to have collisions because we now have an explosion of different kinds of operating systems, especially a lot of sort of user-created operating system implementations. So 1 byte for specifying the kind of a partition is terrible. We need more ways of uniquely identifying operating system partition types. And so now everything is done through these globally unique IDs, and they're standardized so that the potential for collision is exceedingly low. All right, a few other things. Yeah, 128 partitions, each one of them being, like a monstrously huge thing. So should be no problem. The way that GUID partition tables maintain sort of backward compatibility is they plop this thing called a legacy MBR into the first sector with a single partition that covers as much of the disk as is addressable, and the partition type is set to something that OSs will not recognize. Ideally, this means an MBR tool will not corrupt the GUID partition tables. Okay, it's a good try. Also, disks with GUID partition tables would have 2 entries, one at the beginning and one at the end. This is an interesting little detail here because if you have a spinning magnetic disk, they tend to fail slowly, and you can tell that they're failing because they fail incrementally. And so if you can't access the partition table at the start, you can always access the partition table at the end. The only problem with this technique is that solid state drives don't fail incrementally. By and large, they fail all at once catastrophically. So this was a great idea, but not very useful anymore because now we have storage devices that when they go, they take everything at once. And that's kind of a frightening world to live in. I don't know how many of you have thought about that. I hope you make backups of your systems. Okay, and like I say on the slide, most modern operating systems, in fact, I should probably just update this to say all modern operating systems can use GUID partition tables. Okay, it's so common now. I've been doing this class for over a decade, so that's why some of the slides are a little hedgy in their wording. But now I would expect all OSs and all computers that you buy will have firmware that supports GUID partition tables by now. You have to get it used to find something that doesn't. Okay, so this is part of UEFI, and yeah, so this is all just blah, 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 blah. The one thing I want to mention is it sounds like UEFI is this amazing thing. And compared to BIOS, compared to the old world in which everything used to live, it's totally better. But the problem is UEFI is this massive firmware layer, and it's in firmware. So if you have bugs, it's hard to get people to update it. I mean, think about your grandma running a computer with UEFI, and there's a UEFI bug. How do you get your grandma to reflash the firmware for UEFI? The bottom line is you kind of don't. And so this is one of the things that sort of emerged early on with UEFI is that people writing bootloaders, there's this great talk on YouTube by one of the guys who works on Grub, and his efforts to support UEFI. And he's like, there's this bug and this exploit and that exploit. And how do you fix that when it's deployed on millions and millions of computers in firmware? You can't just push OS updates because it's below the OS. So this is a major problem. There are definitely major problems with UEFI. But the nice thing is there's fewer problems, and it's a nicer world than BIOS. And it definitely makes it nicer to write operating systems, although still bewildering at times. Anyway, but this is sort of the wave of the present. That's why I definitely want to mention it. Okay, a few more details and then we'll wrap. So if you want to read into any of these things, you can access the UEFI standards. Tiano Core is sort of the most widely used implementation of UEFI. It originated in Intel and then became an open source project, and there's a whole community built around it. And you can download the EFI development kit version 2 if you want to write UEFI components and tinker with that kind of stuff. I've always wanted to, but I don't think that's the direction 124 will go, because writing a 64-bit operating system on Intel is hard. And I think a better target platform would be a Raspberry Pi, to be honest. Okay, blah, 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 blah. You can F up your Mac if you want to. Don't. And I would strongly encourage, if you want to tinker with UEFI, use VirtualBox because it has UEFI support. Okay, that's all I wanted to talk about with this stuff. Just to mention coming attractions. Next time we're going to start talking about all the material that will be necessary for the first Pintos project, CS124 project 2. So that's what we'll pick up on Friday, and then next week we'll really start getting into the meat of it. So I will see you next time.